Welcome to section 1.1 day 3, sandwiches and speed. Objective, evaluate limits using the sandwich theorem and calculate average or instantaneous speed. So sandwich theorem is also called the squeeze theorem. Average and instantaneous velocity. So the average rate of change, your average velocity, is your change in y over your change in x. And we can find this by taking the f, the function, time plus delta time, minus the initial time, f of t, all over the change in time. You will also see it with h denoting elapsed time as f of t plus h minus f of t over h. For instantaneous velocity or instantaneous rate of change, the velocity at an instant of time, we need the idea of a limit. So here we go. A rock breaks loose from the top of a tall cliff. What is the average velocity during the first 2 seconds of fall? And we're given that the velocity is given by y equals 16 t squared feet in the first t seconds. So we're doing this from the average velocity for in the first 2 seconds. So our initial t is 0, because we're starting at 0 seconds, and our delta t is 2. So we're first going to take the function, this function, and we're going to put in 0 plus 2 for t squared. I have 16, 0 plus 2 squared, minus 16 times our initial time, which is 0, all over our change in time, which is 2. This is my delta y over delta x. And when we do this, we get 16 times 4 minus 0 over 2. This is 64 over 2, which is 32, and this is feet per second. That is my average rate of change. We're taking our initial time plus our change in time for that first function minus the initial time all over the change in time. This is average velocity. Now what happens when we want to find the instant when t equals 2? So now we're looking for the instantaneous velocity. Well, our h would be 0 because we're going to do a limit as we get closer and closer to 0. We cannot divide by 0, so what do we need to do? We expand the numerator and we simplify. So delta y over delta x is 16, and then we put 2 plus h into our function, square it, minus 16 times 2 squared, our instantaneous time, and then over h. And then we expand our 2 plus h squared it becomes 4 plus 4h plus h squared. We simplify further, and now we combine our like terms, and we are left with 64h plus 16h squared over h. And we can factor out an h, and after we factor out an h, we can cancel the h's, and we're left with 64 plus 16h. This becomes a limit as h approaches 0 of 64 plus 16h. So when we put in 0 for h, we get 64 feet a second. This is my instantaneous. So this whole time we're doing this, we are going to be taking the limit as h approaches 0. So when we do these instantaneous changes, we are actually finding the limit as h approaches 0. So remember to put that notation while you're running through this. But the limit as h approaches 0 is our delta y over delta x. Run it all the way through the system, and then when you get at the end, we have the limit as h approaches 0 of 64 plus 16h, which is 64 feet per second. Last thing we're going to look at today is what we call the squeeze theorem, or also called the sandwich theorem. There's many different names for this, actually. The two most common are the squeeze or the sandwich theorem. We can find the limit of a function at a point C by sandwiching it between two functions that have that same limit at C. So here we have a blue line on the top and a green line on the bottom. They are both approaching 1 as we approach 0. on our x-axis. They're both going to 1. And you'll notice the red function is sandwiched or squeezed between them. If we can prove that the limit of the green line and the limit of the blue line are both going to the same place, that means the line that's sandwiched between them must also go to that same place. This is what it says on the right side. It says, if g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit as x approaches c of g of x, the green line, is the same as the limit as x approaches c of h of x, which is the blue line, then the limit of the function as x approaches c of f of x equals the limit as x approaches c of g of x, which is equal to the limit of h as x approaches c of h of x. And that basically what this is saying is if the two outer limits are the same, then the one between them must have the same limit. And this is the squeeze or sandwich theorem. So it says here to use the squeeze theorem to find the limit. Here we have the limit as x approaches 0 of x squared sine of 1 over x. We want to use the squeeze theorem to find the limit. To do this, we should know that the sine of 1 over x, if you put in numbers for x, the sine function is bound between -1 and 1, as long as we aren't changing anything with the amplitude and there's nothing multiplied in front of sine x. We know that sine of 1 over x, we know the sine of 1 over x has to be between -1 and 1. Okay, this we know. We then can use some algebraic properties by multiplying everything by x squared. Then we have -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. Then we take the limits of our outer functions as x approaches 0 of -x squared equals 0, and the limit as x approaches 0 of x squared is also 0. Since these two limits equal each other, and it equals the limit as x approaches 0 of x squared, then by the sandwich theorem, or squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is also 0. This is a basic construction for most squeeze theorems. You have your parent function here in the middle, or your main function in the middle, and you try to work with something you know about it, and then you expand it to make it the whole function like I did here with the -x squared less or equal to x squared sine of 1 over x less or equal to x squared. And we use what our limits are on our outside functions to show what the limit is of the inside function. That is the basic gist. We do the same thing here with limit as x approaches 0 of x cosine of 1 over x. We know that the cosine function is also bound between -1 and 1 as long as we aren't changing the amplitude. So when we do this, we have -1 is less or equal to cosine of 1 over x, which is less or equal to 1. We then multiply this by x, so we have -x. -x less or equal to x cosine 1 over x less or equal to x. We then take the limits of the outside functions. Limit as x approaches 0 of -x equals the limit as x approaches 0 of x, which equals 0. Therefore, by squeeze theorem or sandwich theorem, so by the squeeze theorem, the limit as x approaches 0 of x cosine 1 over x is 0. This is how you have to do these. Yes, you need to show the steps. Show that you have, break that function down into something we know the limits of or what it's bounded by, and then we find functions that we can multiply into it. So it equals the initial function, And in this case, I had to multiply by x to get that negative x less than or equal to x cosine of 1 over x less than or equal to x. Find the limits of the outside functions, and that shows that the inside function is squeezed or sandwiched between them and has the same limit. That is all for section 1.1 day 3. Remember, when you're doing your average speed and instantaneous speed to show your work. And when you're doing your instantaneous speed, notice how we're doing the limit as h approaches 0. So make sure that is in your notation. Thank you for watching and have a nice day.